Should science and maths be taught together using a cross-curricular approach? So what is a cross-curricular approach? Cross-curricular teaching involves synthesising the teaching of subjects together thematically, while discrete teaching approaches subjects separately. Kelly 2012 highlights the latter style of teaching places emphasis on essential knowledge that children need to learn, while a cross-curricular approach helps children to make sense of the world they live in. Both aspects hold importance as children need to access knowledge, but most importantly be able to apply it. So why use a cross-curricular approach? Ofsted 2002 argue it allows opportunities for children to apply knowledge and skills learned in one subject to others as means of consolidation and application of knowledge. Carey 2010 agrees if you want pupils to think, integrate, as integration is more effective in producing cognitive outcomes, and it makes the place of the learner central rather than the place of the content. Most importantly, Ofsted 2008 identified that a cross-curricular approach to learning improved test results and social development when performed with detailed planning and rigorous self-evaluation. So why not? Alexander et al. Argue that learning can become superficial and fragmentary, while Jarvis and Laurie second this view in the light that tenuous links are made between subjects which can lead to artificial and contrived learning, a valid view to poorly planned cross-curricular teaching. Kelly's view echoes that there is the need to ensure that links between subjects are authentic, because if a subject does not fit logically into a theme or topic, skills and concepts may not be adequately addressed. What does this mean for maths and science specifically? Kelly 2012 argues that findings from the Space Project 1990-95 show that learning in science is most effective when children are able to see the relevance and when it is meaningful to them. This view is applicable to maths, as Kelly 2002 argues there's a disconjunction between maths for the classroom and in everyday life, and a need to link this to world experience. Science allows real-life application of maths, and in turn, maths provides means of discussion and evaluation for science. As Henry 2012 argues, much of science uses the language of maths to explain our world. There's clear overlap between the two subjects in the curriculum. I'll be focusing on measurement in the maths curriculum and linking to plants and states of matter / properties and changes of materials in the science. So how does science and maths link? During my placement with the Year 4 class, I engaged with the Cornerstone scheme, which plans curriculum coverage through topic work. Interestingly, literacy and maths were taught discreetly, reflecting Ofsted findings in their 2008 survey that found 7 out of the 12 schools surveyed used a thematic approach, but also taught subjects discreetly for part of the time, especially literacy and maths. This could be linked to the demands of national tests and SATs. During a potions topic, I taught lessons involving measurement of liquids and solids to create a potion, in which pupils mixed different amounts and combinations of solids and liquids and observed, did some ingredients dissolve, react, what happened when more of something was added. This links the states of matter and properties and changes of material sections of the curriculum with the measurement area of maths, which informed variables and provided the language for explanation and prediction, reflecting Henry 2012's view that the language of maths and numbers enable children to discuss their findings. Across working scientifically areas of the science curriculum, children are expected to plan inquiries, gather and record data, take accurate measurements, and evaluate and record findings using simple scientific language. This coincides with the measurement sections of the maths curriculum, as from Year 1 onwards the requirements are to measure height, length, mass, weight, capacity, volume and time with use of rulers, scales, thermometers and measuring vessels, the same equipment required in science. Henry 2012 identifies this connection between scientific inquiry and the application of practical maths skills as appealing holistically to the whole child and giving learning context. Henry also highlights the national curriculum stresses the importance of collecting evidence in science when trying to answer a question, and maths is often the medium for that collection, further cementing the intrinsic overlaps between the subjects. He favours a constructivist approach which encourages lessons which begin as problems, not as a set of instructions, as communication and reasoning are integral elements of both scientific and mathematical experience. This aligns with the constructivist theory of learning and Piaget's principles discussed by Jordan and Carlisle 2008, which suggest that teachers should nurture children's natural curiosity, provide physical and interactive and manipulative material, and create opportunities for exploratory classroom discussion. Jordan and Carlisle also discuss trivial constructivism, which recognises learners personally interpret information they receive through discovery learning and peer talk and interaction. According to Piaget, children must go through the process for themselves, and teachers must not impose ready-made solutions that children will accept without making the knowledge their own. Carey 2010 agrees that low-order tasks require passive reception and parrot-like repetition, whereas higher-order skill requires pupils to manipulate data. This mixture of mathematical deciphering alongside scientific discovery allows children opportunities for higher-order response. Take measurement in the maths curriculum and plants in the science, for example. Hendry argues that the study of plants raises many questions of what to measure, how and when, therefore the possibilities are limitless, but the mathematical application of measuring and data analysis is clear. Carey argues that to fully understand the problem, children need to draw together insights from different subjects, and discrete teaching only offers partial insight. The Year 2 programme of study on plants states children should observe and describe how plants need water and light and a suitable temperature to grow, and also how seeds and bulbs grow into mature plants. Children can describe these circumstances without mathematics, however, the use of maths gives children access to more accurate, comparable results and gives their maths a living context. So, authentic overlaps in the maths and science curriculum are clear. However, pedagogical responsibility of schools and teachers can cause implications for cross-curricular teaching. In 2005, Fricon and Glasson performed a study with trainee teachers which identified that the skills required for successful cross-curricular teaching should be taught and aren't always during training. They argue that teachers need both content and pedagogical knowledge to teach maths and science, including classroom knowledge of their space and learners, professional knowledge of the curriculum, academic knowledge about the nature of the subjects, of which both are broad and complex, and these can pose unrealistic expectations, especially for new teachers. Their opinions are echoed by Kelly 2012, who states many teachers have received little or no training in designing the curriculum. Fricom and Glasson also argue that the terms integrated and interdisciplinary suggest a seamless mixing of subjects, which is problematic. Instead, we should consider links situated authentically in the respective practices of each field. This is more possible for teachers. All novice teachers in the study argued that connecting maths and science seemed intuitively obvious. Hendry 2012 goes as far as to argue that the discontinuation of the Key Stage 2 Science SAT in 2009 saw a loss of status for primary science, and links to maths bring science back into the educational limelight. He claims the two form a dynamic partnership that will increase confidence and clarity of learning in both areas at the expense of neither. However, as worthy a partnership as the two may be, Dunn and Peacock 2012 highlight that class size and behaviour management during experiments and practical work hinder success, and the merging of the two subjects presents difficulty in individually assessing learning in each. Carey 2010 echoes worries that too few teachers have a genuine command of explaining, questioning, task setting and differentiation in cross-curricular teaching. And Ofsted 2008 highlight that barriers also include anxieties about negative impact on exam results and a lack of continuity across the schools, moving towards SATs where maths takes priority. Following a fluctuation of changes from more free topic-based teaching in the 80s, past the introduction of the national curriculum in 1988 in an attempt to standardise discrete teaching across schools, to the freedom organisations have today in delivering curriculum coverage, it seems in relation to maths and science, authentic links exist that benefit both subjects. However, they can't account for the entire curriculum and subject-specific skills and knowledge. As Alexander 2010 and Rose 2009 contest, a combination of discrete teaching and well-planned cross-curricular themes is essential. Before I conclude, I'd just like to discuss ICT as a third subject which can be used beneficially to enhance the teaching of science and maths cross-curricularly. Rose and Howard suggested in regards to the 2009 national curriculum that ICT should be integrated across other subjects purposefully. Howard et al. 2011, however, stressed that ICT must be carefully planned and directly linked to intended learning outcomes. Therefore, science and maths must always take priority, and ICT shouldn't replace hands-on lessons. Howard et al. Also identified the benefits of ICT integration, such as use of data loggers, CD-ROMs, digital microscopes, interactive whiteboards where experiments aren't possible to share simulations and videos, findings, graphs, and visual aids. The Internet also allows for research and use of interactive websites, for example NASA. Databases like Excel and TextDo's can also be used to present findings on graphs easily and quickly. Howard et al. Recognise that this enhances children's scientific questioning, evaluative and observational skills, and requires them to think carefully about which information to include. These graphs can be added to and compared over time and interrogated against other findings. Finally, cameras and iPads can be used as a form of documentation, as I used in my own capacity lesson. Children can take pictures and videos of reactions to observe more than once and to share with the class and compare. They could also be used to document plant growth, taking a series of pictures over time and much more. Crucially, teachers need to have a strong competence in OCT and be wary that it should always be in support of the science and maths objectives. Again, used in the right way, unforced and informatively, ICT can be supportive to teaching and learning in science and maths.